So today we're going to do an example of using the technique of integration by decomposing via partial fractions. And in this case, we're going to have a quadratic factor. The last example, we didn't have a quadratic factor. So the idea here is to rewrite this rational function. Well, first let's make a note of the fact that the rational function happens to be proper. The degree of the numerator is 1, and the degree of the denominator, when you multiply it out, is 3. So we don't have to make it a proper fraction. So we're going to rewrite that. We're going to separate that into simpler fractions. So we've got it fully factored. You should note that the factor x squared plus 2 doesn't factor anymore, right? That's always bigger than 0. So we've got it fully factored, and one of the factors is quadratic. So the goal here is to write it as a sum of two fractions, also proper fractions, with these factors as their denominators. But we want to make the numerator as general as possible and keep them proper fractions. So for the x plus 2, well, that's not really an issue because it's a linear. The biggest the degree of the numerator could be and have it be proper is 0. So that's got to be a constant in the numerator. So that's why I've got an a there. But for the x squared plus 2, that's a degree 2 polynomial, so the numerator could have could be linear polynomial. It's possible the b might be 0. I mean, there might be a situation where the b zeroes out, but the most general form would be a linear polynomial. And so now the idea is these two fractions add together to give us the original fraction. So let's add these. Of course, the common denominator is exactly that denominator that we started with. And in the numerator, I'm going to get a times x squared plus 2 plus bx plus c times x plus 2. So we want to find a, b, and c so that this fraction here, that added together one, is our original fraction for all x, for which that's defined. Now the fractions are not defined at x equals minus 2. However, in order for those to be equal for all x except for x equals minus 2, the numerators have to be equal for all x. So two polynomials can't differ at only one point. So they've got to be equal for all x. Thus, we can plug in various values of x to determine what. So let's do these in different colors. To get equations to solve for a, b, and c. So we're going to need a total of 3 different equations because we have 3 unknowns. So I'm going to try making an equation by plugging in x equals -2 first. Why am I doing -2? I'm doing -2 because that zeroes that out, right? Well, let's actually write out what we have here. We've got 2x plus 1 is equal to the numerators. The numerator of the left fraction is equal to the numerator of the right fraction. And I'm going to try now setting up one equation by plugging in x equals -2. And that's going to give me, when x equals -2, I'm going to get -2 times 2, that's -4 plus 1, -3, is equal to 6a. And the whole point of plugging in -2 is that that term zeroes out, right? So I don't have to worry about that term. And that gives me a equals -1/2. Okay, and what's the other thing I'm going to plug in? Okay, so I've got a equal -1/2. So let's plug in, let's try a different color here. Let's try blue. Well, the thing is this quadratic factor, the whole point is that doesn't factor, right? So there's nothing I can plug in to zero that out. But if you notice, I might be able to plug in something to zero out of that b. If I try x equals 0, that's a good thing. So let's go with that. So if I try x equals 0, then on this side, 0 plus 1, I get 1. A is equal to minus 1/2, so I can plug that in. Minus 1/2 times 0 plus 2, that's minus 1. B zeroes out, and when I plug in 0, I get 2c. And so that's going to give me c's equal to, add 1 to both sides, divide by 2, I get 1. Okay, and then finally we need to plug in something else. What color am I short on? We need a purple here. Well, there's nothing else that can be zeroed out, so I'm just going to plug in a nice simple number. Let's call it x equals 1. If I plug in x equals 1, I get 2, 3. A is equal to minus 1/2. 1 plus 2, that's minus 3/2. And b, we don't know. That's what we're looking for. I plug in 1, I get b plus 1 times 3. 3 times b plus 1. And I can divide by 3, I get 1 is equal to minus 1/2 plus b plus 1, or b is equal to 1/2. Okay. And so at this stage, what do we have? We've been able to rewrite the integrand as a sum of two easier functions. So let's do that. We're going to have it as a sum of a over x plus 2, and a being negative 1/2, so that's negative 1/2. The integral of dx over x plus 2, and then plus bx plus c over x squared. So that's going to be the integral. B is 1/2, x, c is 1 over x squared plus 2. So now let's move this partial fractions decomposition out of the way, and so we have some more room to work. So now let's look at the integrals we have here. This one here, this dx over x plus 2, well, technically you can use a u substitution, right? U equal x plus 2. But of course du then is only equal to dx. It's pretty easy u substitution. And as I mentioned in class, that if you use a linear function, you should try to get used to being able to do that in your head. So if I try to do that in my head, I'm going to get, well, what is 1 over u, the integral? It's ln absolute x plus u, x plus 2, ln of that u. And the derivative of that x plus 2 is just 1, so I don't have to even worry about the constant here. And for this other one, I'm going to pull out the 1/2 just to make it a little bit easier. So I'm going to get 1/2 integral x, and that 1, oh, I forgot the dx here, so sorry. Okay, in that top integral, I forgot the dx. So then when I pull the 1/2 out of the 1, well, that's going to leave a 2 here, right? Because 2 times 1/2 is equal to 1. And that's x squared plus 2. Don't forget the dx this time. Okay. So how do we approach that? Well, we discussed this in class 2. We're going to separate this. It's a linear in the numerator, but it's not a linear we can do a direct u substitution for. So we're going to separate that into two separate integrals. So we'll write that as negative 1/2 ln of, well, this I'm just repeating, right? And now I'm going to separate this into the integral of x dx over x squared plus 2. plus the integral of 2 dx over x squared plus 2. Of course, the 2 and the 1/2 cancel, but I'll do that in the next step. Okay, so what does this gain us? Well, let's use some, I like purple writing here. This one, well, this one can be a u substitution, right? U equal x squared plus 2, because we've got an x and an x dx up there. So if u is equal to x squared plus 2, du is equal to 2 dx, 2x dx, or 1/2 du is equal to x dx. Okay, so that x dx is 1/2 du, so we're just going to have 1/2 of du over u, right? And this one, I'm gonna simplify it a little bit. Of course, we can cancel the 2's there, but the 2's will definitely cancel. But let's look at that denominator. If I write x squared plus 2, I can pull out a 2, right? And that's going to be 2 times x squared over 2 plus 1. And then I can pull that 2 into the square, that 1/2 into the square, and I get 2 times x over the square root of 2, quantity squared, plus 1. So that is going to, rewriting the denominator as that, it's going to make it look a lot more like an arctangent problem, right? So this is now equal to, well, it's negative 1 over 2 ln of x plus 2 plus 1/4, right? Because 1/2 times 1/2 of du over u plus, I'm going to pull that 2 out, that 1/2 out, so I'm going to get a 1/4 here. Oh, but the 2 cancel. Let me erase that 1/4. And note, this 2 cancels with that, so I'm just going to have that 1/2 there. Oops. So that's going to give me 1/2 integral dx over 1 plus x over square root 2, the quantity squared. Okay, we're almost ready to go here. So this is equal to then 1/2 ln x plus 2 plus 1/4 ln absolute value u, right? We'll change that over. And what's this other one? Well, it's going to be 1/2 times. So we have, this is an arctan of x plus x over square root 2 integral, right? Basically, and let's figure out what that constant is that we have to multiply it. Arctan of x over square root 2. Of course, when I take the derivative of that, I'm going to get the derivative of x over square root 2, which is 1 over square root 2, so I need a square root 2 to cancel that. Since that's just a linear factor, we don't really need a formal u substitution, although you could do it that way. And of course, we have the plus c. And there we have it, our answer. I'll let you guys check it at home. Oh no, we're not done yet. What do we need still? Right, we need to replace that u. Oops. 1/2 ln x plus 2 plus 1/4. What's our u? Our u is x squared plus 2. That happens to be always positive, so we don't have to have the absolute value there. And there, now we finally have it. Ignore that first one. this is the answer. We've got it all in terms of x, and now you can double check it at home. Goodbye.